Welcome everyone to Wednesday Night at the Lab. I'm Tom Zinnan. I work here at the UW-Madison Biotechnology Center. I also work for UW Extension and Cooperative Extension. And on behalf of those folks and our other co-organizers, Wisconsin Public Television, the Wisconsin Alumni Association, and the UW-Madison Science Alliance, thanks again for coming to Wednesday Night at the Lab. We do this every Wednesday night, 50 times a year. Tonight, it's my pleasure to introduce to you Luke Zoet. He's an assistant professor in the Department of Geosciences here. He's a glaciologist. He was born in Grand Rapids, Michigan, and went to high school in Caledonia, Michigan. Then he went to Michigan State for his undergrad in geophysics, moved over to Penn State to get his master's and PhD, both in geophysics. Then he went to Iowa State for a postdoc for about 3 years, and then he came here to the UW-Madison in 2015. In addition to his appointments in geoscience, he also has appointments with the American Indian Studies Program and the Geologic Engineering Program. Tonight, he gets to talk to us about something very appropriate for the snow we just had and the ice we will soon have. He's going to talk with us about the mysteries of glacier slip and landform development. Glaciers are pretty important to those of us here in Wisconsin. They came, they left, and they left behind a good chunk of what our landform is like now. And so I'm interested in hearing what he has to say. He's also gone to Antarctica and Switzerland, which are more exotic places in Wisconsin. So I hope we get to see more about stuff like that. Please join me in welcoming Luke Zoet to Wednesday Night at the Lab.
Well, thanks for having me here. I'm really excited to talk about some of the work we've been doing. I thought I'd start out just talking a little bit about this picture I have on my opening slide here. So this is a picture of the glacier called the Lech Glacier in Switzerland. And what you're looking at is basically a big chunk of ice. It has a high part sort of in the upper right here, and the ice sort of slopes down to the left, where it moves downhill. If you were to go out and look at this glacier, you would probably not really see anything. It's basically sitting there. But if you watched it for a long enough time, sort of years or decades, you'd see that it actually is moving at a really slow rate. The reason it's moving is because of that slope at the surface. So a river, a glacier in a lot of ways is like a river. There's a slope at it, along it, and gravity is sort of pulling the glacier downhill, down the slope. The mechanics that sort of govern how a glacier moves are quite a bit, in some ways quite a bit similar to how a river works, but in other ways they're quite a bit more complicated. If we were to look at a glacier like this from space, for a long enough period of time, you could begin to see sort of similarities between the motion of a glacier and a river. So you have sort of, this is a glacier in the Karakoram region in India, and we're sort of looking at it for about 30 years, and you can see ice is sort of being advected from this region that's in a higher elevation to regions that are a lower elevation. The ice is grinding up the material that it's sitting on. It's sort of incorporating it into the ice, and it's advecting it down ice. Eventually, when it gets to the end, or what we call the terminus, the material that it sort of collected is being deposited and just dumped out in these big piles called moraines. When you look at this picture, though, you get a sense that it's moving, that at least the top of it's moving, but how is it moving, and why is it moving? What are the processes that are allowing it to move, and what is it doing to the rocks that it's sitting on when it's moving? Because this glacier, it might be a couple 100 meters thick, but at the bottom of it, it's sitting on just rocks like you might see on the sides. When people first started to look into this, the field was in the early 50s. So glaciology, with respect to most sciences, is a really young science. It's only been sort of developed since the 50s. And it was started by sort of physicists and mathematicians that also just like to go climb on glaciers. So they said, well, we can study these. You know, it's a relatively open field. And the real sort of pioneer that started working on it was a physicist by the name of John Nite. And he did some seminal work in the early 50s to try to explain why the ice would flow down a hill like we see there. And this is a figure from his original paper. And what you're seeing here is a schematic if we cut the glacier in half and we looked at the side of it, right? So what this layer at the top would be the surface. If you were to stand on it, you'd be up here. Then this below is all ice. And then this lower line would be the bed. So this is ice and below it is rock. And so they're at some slope, and so the glacier is sort of moving down the slope with time. If you came here at some point and you drilled a vertical hole from the surface all the way down to the base, and then you waited some period of time, say you waited 10 years, you'd come back and what you'd find is that hole had moved down the hill a little bit and it had been bent a little bit. Well, what John and I did was he used some experiments that people had done very early on to look at how ice deforms. And based on how the ice deforms, he was able to calculate how much of the total motion of the glacier moving down the hill should be from deformation of the ice. Just like how in a river, the water moves because it's deforming, and the water at the bottom is basically not moving at all, and as you move farther and farther up the river, the water deforms more and more. And when they did that, they back projected it, and they said, well, only this component of forward motion, this small part, is actually from deformation of the ice itself. In reality, the majority of the motion was from the ice sliding over the bed. So there's this extra component that people didn't really realize existed until John and I started to sort of apply a mathematical theory to this, and that's this UW component. So the forward motion that we see from the surface in that first image, from the satellite photos, is composed of two things. It's composed of this basal sliding and then also deformation of the ice. This is sort of akin to if you took an ice cube and you put it on a board and you lifted the board up and it was on a slant. The ice cube would deform a little bit. You probably wouldn't even see it, but it would deform a little bit. But the ice cube would slide down the board over time. And that's basically what these glaciers are doing. In response to the ground being slanted and the surface being slanted, they're sliding down the mountain over time at a really slow rate of speed. And the thing that's holding them back from just shooting off the board is also the bed. So there's this balance between the bed holding the glacier back and gravity trying to pull it down. And as a result of those, there's some motion of the glacier moving forward. So why is this important? Well, one reason it's important is the Intergovernmental Panel on Climate Change has listed our lack of knowledge of basal processes as one of the key uncertainties in our ability to understand and project how ice flow will occur. So if we look at the large glaciers in Antarctica and things like that, they're sort of moving ice from the interior of the ice sheet out towards the coast, where it then gets dropped into the water. And when we hear, climate change is occurring and things are warming up and glaciers are melting, well, the primary way the glaciers are losing mass is not actually through the ice melting up on the surface of the glacier. It's because more ice is being dumped into the ocean and it's melting in the ocean as it's floating around. And so if we want to know how much ice gets dumped into the ocean, we really have to know how fast the ice is moving towards the ocean. This is a map of ice velocity in Antarctica. So the color scale on the continent here corresponds to the velocity, where the purples and the reds mean it's going quite a bit faster, and these sort of darker colors means it's not moving very fast at all. And what you see is there's some areas like here and here where the ice is moving exceptionally fast, sort of up to tens of kilometers a year, 10 kilometers a year. And it's in those areas where the ice is moving really fast that it's able to discharge a lot of the ice to the ocean. These circles represent the mass balance of the region. So is that sector of Antarctica losing mass or is it gaining mass? If it's losing mass, that means all that mass it's lost is going into the ocean and contributing to sea level rise. And so this sector over here has this big red circle, meaning it's losing mass. And the reason it's losing mass is because the ice is quickly flowing into the ocean, be deposited and breaking off in the ocean as icebergs, and then it melts around in the ocean. So to understand how much future sea level rise we might get, we have to have really good predictions of how fast glaciers will slide, because that's the main thing that contributes to them adding ice to the ocean and leading to sea level rise. If you had a sector like this of West Antarctica and Greenland, which are areas that are really susceptible to high rates of glacial glaciers transporting ice into the ocean, you could have potentially a collapse of these areas, which would lead to quite a bit of sea level rise. In West Antarctica and Greenland combined, there's something like 12 meters of potential sea level rise. And so this is just a really simple treatment. All I've done is take a map of the southeast of the United States and colored everywhere that was below 12 meters in red. So these are areas that are particularly vulnerable if sort of areas of West Antarctica or Greenland started contributing more and more ice into the ocean. If you were to take into account all of East Antarctica and the Greenland ice sheet, you're looking at a much greater number, 68 meters of sea level rise. Now, this is highly unlikely to happen because East Antarctica is really stable. But the point is to be able to make projections about when things like this might happen or how likely they are to happen. We have to have the physics of how the ice is moving down the hill, down the slope, very accurate. Otherwise, we're not going to be able to make very accurate predictions about how likely stuff like that is to happen. So if we go back to this simple diagram, the basic problem is this component, how much the ice slides down the hill, is really hard to figure out. You know, you could tell me, if you could tell me you had a glacier that was a certain thickness and had a certain slope, and you asked me, okay, you tell me how much it's going to move in a given year, that's a hard question to answer because we don't know the physics of these basal processes very well. One reason is because in a lot of cases they're under kilometers of ice and it's really hard to study them directly. And another is just because it's a very complicated area. You have ice with water sitting on rocks and all the things are interacting together in a very sort of complicated manner. So the whole talk is basically going to focus on this small area right here, right where the ice sits on the bed that's beneath it, and what happens when the ice moves or slides over the bed beneath it. We're only going to be concerned with sort of a couple feet above that and a couple feet below it, because frankly that's where all of the action is, and that's where our big lack in knowledge of being able to predict how glaciers work stems from. So the main question of this talk is, how does ice slip over glacier bed, and how does that affect the bed? So there's a sort of reciprocal relationship. As the glacier is sliding over the bed, it can also do things to the bed. It can break it up. It can pick up dirt from one area and deposit it in another area. It can sort of conveyor belt material out of the area entirely. So there's this sort of feedback between the two. This is a glacier in Norway called Ingebreen. Just for your reference, this is actually the glacier up here, and this is a region in front of the glacier called the forefield. And the forefield is the area in front of the glacier, but behind sort of the maximum extent of the glacier. So that area, the forefield, used to be under the glacier, and the bed under the glacier right now probably looks a lot like the forefield, probably pretty much the exact same. If you look at it, it doesn't look perfectly smooth. It doesn't look like a board, right? It has all these bumps on it. So one question is, why does it look like that? You know, what are the processes that occurred at the bottom of the glacier that caused whatever there was before underneath it to be shaped into something like this? Well, a glacier has sort of two primary ways that it shapes the bed that it's overriding. The first is a pretty simple concept, but it's very powerful. It's something called abrasion. And all it is if you think of the bed of a glacier and the ice above it can have rocks embedded in it, right? It's not always perfectly clean ice. A lot of the times there's big clasts and things like that in the ice. Sometimes they're up in the ice column, but sometimes those clasts are in direct contact with the bedrock below. And when they're in direct contact with the bed below, they can be pressed onto the bed. Once they're pressed on the bed, as the ice slides or moves forward, it sort of drags the rocks along the bed, and it creates these sort of scratches, or what they're called striations is the term we use, in the bedrock as a result of the bed being scratched by the material that's in the bed. This is basically akin to sandpaper. So if you have a block of sandpaper and a piece of wood, if I put the sandpaper on a piece of wood and I rub it, it's going to sort of scratch up the wood. It's going to smooth it out over time. If I move it really fast, I'm going to be able to sort of sand the wood at a greater rate. If I push really hard, I'm going to be able to sand the wood at a greater rate. Or if I have sort of more little grains of sand in the sandpaper, I'm going to be able to sand the wood really fast. And so abrasion works the same way. It's basically class in the bed of the basal ice being scratched against the bed. People have noticed these for a long time. Some of the seminal work was done by T.C. Chamberlain. He was a glacial geology in the geoscience department here. He then went on to become the president of the university. Even though I'm sort of filling his shoes, I can assure you I'm not going to become the president of the university. But we do have a long tradition of geologists at Wisconsin becoming president of the university. But one thing he realized is that these scratches in the terrain, these striations, give some indication of where the ice is flowing from. And so he went around the upper Midwest, and he figured out where all the striations were, and he was able to reconstruct the origin of the glaciers and how big the ice sheet was. And that's where he got the idea of this continental scale glacier called the Laurentide ice sheet. But abrasion will take a bumpy terrain and smooth it out, just like if you had a bumpy piece of wood and sandpaper would smooth it out. If you zoom into one of these abrasions, they look something like this. So at the end of my finger here is a really fresh abrasion. This is something that, that probably was covered by the glacier just the year before. And so this was one big rock pushed into this limestone and drug across it. The limestone has the benefit of it's black, but when you scratch it up, it turns white, so it looks really dramatic. And you can sort of see this this rock as it was pulled across. And there's a lot of other different striations in there. Here's another set of striations. You can see the up ice side of the boulder to the left here has been sort of smoothed out as the ice has flown around it and the glaciers have scratched it away. Here are sort of newly born or newly exposed striations. This is the actual base of a glacier, and these are the rocks that are under it. So these striations are probably caused by these rocks sitting right here. This is sort of as fresh of a striation as you can get from a glacier up in the Canadian Rockies. So one mechanism for eroding the bed of a glacier and shaping it to look like that is this abrasion process. The second mechanism that really is effective is something called quarrying. So quarrying depends on there already being bumps in the bedrock. So before the glacier gets there, or for some other mechanism, the glacier already has bumps in it. And you can imagine if you have ice and you're sliding over the bed and you come off of a bump, you might be able to sort of ramp off it. And that's effectively what happens with the glacier, is if there's a bump here, the ice is pretty stiff. And so if it's moving, if it's flowing faster this way, then the ice can flow into the gap behind the bump. You get actually a cavity, a pocket that forms where there's no ice. A lot of the times the pocket fills up with water. Most of the time it does. But what happens is you have these sort of cavities that regularly form behind, or what we say in the lee, or behind bumps in the bed. This is an interesting phenomenon because the presence of cavities at the bed of the glacier basically means that the region underneath the cavity cannot support any of the weight or hold the glacier back at all. And that all of the weight and all of the resistance to sliding has to be loaded on this small piece right here where the bed is actually in contact with the glacier. And so you have an area with a lot of stress, with a lot of weight on it, where the ice is in contact, immediately adjacent to an area where there's very little stress. Because this cavity has formed and basically stress can't be imparted on the bed by the weight of the overlying glacier. And that big contrast in stress can cause a fracture to occur. And the fracture will grow a little bit, and then it'll grow a little bit more, and then it'll grow a little bit more. But eventually, it might intercept sort of a bedding plane or a weak plane that already exists in the rocks that are already there. And this block will be plucked away or quarried away. You can imagine that this same process might be happening up here, so you'd have this sort of stair-step pattern that just moves back over time. This quarrying pattern can leave something like this. So the ice is flowing from the top of the screen down to the bottom. These joints here you can see already might exist, or they might be generated by sort of cavities, and these blocks are just being plucked away as the ice is moving back over time. So these are areas that might experience quarrying. Quarrying, as opposed to abrasion, tends to roughen the terrain. So you have abrasion that smooths things out. If that occurs, if quarrying occurs, the terrain gets really rough and sort of jagged looking. This is that previous rock I showed you that had abrasion, but it's also got a signature of coring behind it. And these types of features you can find all over in glaciated terrains where there's bedrock exposed. So in northern Wisconsin, there's good examples of these, and sort of red granite, in the town of Red Granite, there's a lot of exposures of these types of features found throughout the state. Okay, so erosion, these two erosion processes acting sort of simultaneously when the glacier was over this region is what made this bed so bumpy. It's what made it have this shape. And these processes are still going on back behind this region, and they're causing the region behind here to also become more and more bumpy. The bumps are good because if you think back to this analogy of an ice cube sitting on a board that you lift up, what happens in that case? You lift the board up high enough and the ice cube basically just shoots off the board, right? There's nothing sort of, the board isn't bumpy enough. It doesn't have any sort of obstacles for the ice cube to get around, so it just slides off. And in fact, if a glacier had a perfectly flat bed, like a board, and you lifted it up like that and it had some slope, we wouldn't really have glaciers because the ice would just immediately accelerate and shoot right off the side of the cliff or side of the mountain. It's these bumps, these small scale bumps at the bottom of the bed that hold the glacier back. Because if the ice wants to advance, it has to get around the bumps. And so however fast the ice at the bottom of the glacier can get around these bumps is how fast the glacier will flow. If it can get around the bumps really quick, then the glacier will go really fast. If it can't get around them very quick, the glacier won't go very fast. So we have to figure out how glacier gets around the bumps at the bottom if we want to know how these large-scale ice models should work, right? The physics of them is tied to like the physics of how ice gets around smaller features like this. So that sort of rule, that sort of relationship between how fast the ice gets around bumps versus how hard you push on the ice to get around the bumps is something called the sliding rule. So it's how much resistive stress or drag, how hard those bumps push back against the bed, how much resistive stress or drag the bed of the glacier can provide over a range of sliding speed. So if you go faster and faster, does the bed push harder or does it not push as hard? So the objective is to try to determine a sliding rule for these hard bedded glaciers. So by hard bed, I mean the bed is made up of bedrock. It doesn't yield. It's sort of always there. The ice has to move around it. So in the 50s, late 50s and 60s, the first sort of attempt was made at this by a material scientist named Jan Weertman from Northwestern. And what he did was he idealized the bed of a glacier to something like these cubes. He called them tombstones. So this is called Weertman's tombstone sliding model. And the ice is sliding from the bottom left to the upper right. And however fast the ice can get around these bumps is how fast the glacier will slide. And what he said was, well, the upstream side of these bumps have to be under a lot of pressure because they're actually the thing pushing the glacier back. They're the thing holding it up. And the back side of these bumps have to have low pressure. And so the ice can actually flow around the bumps. You've probably all seen this in a different context. If you went out to a river and you threw a big rock in it, the water would move around the rock, right? Because there's a lot of pressure on the upstream side of the rock in the river, but there's not a lot on the back. So the water deforms around the rock and then rejoins on the back. And so that's the same model that Weertman sort of proposed for these tombstones, was that the high pressure side would cause the ice to creep, flow around the back, and then where it would essentially close back up. And the rate at which that happened is how fast the glacier slides. His sliding rule produced a form of a function that looks sort of like this. And you're going to see this type of axis a lot, where this is sliding velocity versus shear stress. So you can think of this as how fast the ice is able to get around the bump versus how hard the bump is able to push back against the bed. So what this is saying is the faster and faster the ice tries to get around the bump, the harder and harder the glacier is able to sort of resist that moving. And this is kind of like driving down the street and sticking your hand out the window and there's air pressing on your hand. And then you double your speed and the air is pressing on your hand twice as hard. And then you triple your speed and the air is pressing on your hand 3 times as hard. That's effectively what this relationship is saying, is no matter how fast the ice goes, the bed can always push back harder and harder and harder to sort of resist it from from accelerating and shooting off the mountain. Another type of sliding law takes into account these cavities that I talked about before. So the ice flows, and cavities form in sort of the lee in the area behind the cavity. The cavities are often filled with water. If we look at a bed that we can sort of idealize as a two-dimensional bed, as a stepped staircase, just like the other picture I drew for quarrying, this rule predicts that you should have a resistance to sliding that's essentially flat. So essentially, as the glacier starts to speed up, it pretty quickly jumps up to some maximum stress that it can hold the glacier back, and then it can't do anymore, right? It reaches this maximum level, and then it's sort of flat, right? This is a different set of ideas about sliding law if we take into account this idea of a cavity. Another sort of variation of this cavity type sliding law is if we had a bed that looks like a sinusoidal wave. You know, you saw that forefield that I showed, and there's different shapes in it. And you might be able to idealize it to a sinusoidal wave or sort of a step geometry or maybe the tombstone type geometry. But if you had a sinusoidal step geometry, again, the cavity grows as the ice starts to speed up, and you get some sort of resistance to sliding. This response is quite a bit different. It says that the glacier can push back as you're speeding up. This is going up. It can push back harder and harder, harder and harder. But then it reaches a point where it can't push back any harder, and it actually starts to get smaller and smaller, the resistance. This would be akin to if you're driving down the road and you put your hand out the window and the wind is pushing on it and you're feeling some resistance, and you're going 10, all right, you go 20, it's pushing back harder, then you go 30 and it actually gets easier, right? There's some mechanism, something else that's going on that the wind isn't even pushing on your hand. And then you go 50 and it's basically not pushing on your hand at all, right? So this would say that these cavities at the bottom of the glacier are really sort of affecting the glacier's ability to hold back the entire weight of the glacier from the glacier shooting off the mountain. Okay, so we have these different ideas. These were all derived by sort of physicists and mathematicians in the 50s. They're very hard to test in the field because you can't separate the variables in the field. Plus, it's very hard to access the bottom of the glacier. So we went essentially 50 years with all these different ideas and nobody ever being able to test them. You can imagine that's problematic because the first one, the Weirtman sliding law, is sort of the main parameter that's put into all ice flow models. So everything you see that predicts sea level rise directly depends on that sliding law and that sliding law being correct, right? That's everything we've seen for sea level rise. That is one of the main equations that it's predicated on. So how do you answer this? How do you answer this part that's hard to figure out? Well, we go to the lab. And we've only been able to do this in the last 5 years because it's only really in the last 5 years that we've been able to make machines complicated enough to actually simulate the bottom of a glacier. This is a large-scale ring shear device. It's housed at Iowa State University. And it basically can mimic the bottom of a glacier. So what you do is you load up this big ring apparatus right here with ice. Well, first you put a bed in the bottom of it. So we put a bed that looks like a stair step or a bed that looks like a sinusoidal wave or something we want to put in to test those various theories. Then you load it up with ice, and then you close the lid down, and the top grabs the upper surface of the ice, and it rotates it while the bottom is stationary fixed. And so it basically forces the ice to slide over a bed, just like we have in those models that we sort of were testing. This whole thing is sunk in a giant tub of antifreeze, and then that whole thing is in a giant walk-in freezer like you might see, you know, behind McDonald's or something like that to sort of really get the temperature regulated. And then this thing spins at the actual rate a glacier moves, so you know, slower, way slower than the hour hand on a clock, and it spins for like 3 or 4 months. You just push go, you sit there and you go and you look at it every day and you make sure something's not broken, and you do whatever else for 3 months as this thing is slowly moving and simulating a glacier sliding, you know, in a cornfield in Iowa, essentially. So we're building one of these at Wisconsin. It's almost done. There's only one of these in the world right now. It's at Iowa State. The second one's being built at Wisconsin. It's got some more bells and whistles, but for most purposes, it's very similar to this one. This is a cutaway, so the bed can be placed sort of in the bottom here. This is a picture of it with the top up, and so it's a very large, impressive device that you know, took a decade to sort of work out the bugs. This got this huge thing is a giant gearbox, and this little thing is the motor. You have to really gear the thing down to get it to spin the rate of a glacier sliding. Right? So here's a cutaway. This is a picture of it with a sinusoidal bed. The ice is held right at what we call the pressure melting point. You can think of that as 0 because the ice at the bottom of the glaciers is 0 degrees Celsius. It's right where it melts. There's stepped and sinusoidal rigid beds made of this material called delrin. And so we can begin to test these ideas. So for a sinusoidal bed, we have these two predictions. We have this prediction Weertman made that's in most ice sheet models, and this other prediction of something called the double-valued sliding law that goes up, and then the resistance gets slower and slower. And the results we find are pretty interesting. They're basically perfectly match this black line, and the black line is the theory from behind this Weertman type, or behind the double-valued sliding law. And they don't fit the Weertman sliding law really at all. It's a bit interesting, right, that this sort of primary constituent equation that we use in ice sheet models doesn't really bear out, the basic physics behind it don't bear out when it's actually tested. So what about for a stepped bed? We have this idea of a function going up, a Weertman sliding law, or something that's completely flat. Well, we actually see a reduction in sliding speed. So something that's sort of contrary to what both theories predicted. So the primary findings from sort of testing these things in the lab are that Weertman sliding doesn't fit any type of the bumpy beds that we tested, and that this rate weakening, meaning that as you go faster, you actually get less resistance, seems to dominate for both bumpy beds. But if I took you back to the field and I said, okay, there's the forefield, that's what the glacier is probably sliding over, and I said, which one of those three things does it look like? You'd probably say, well, it doesn't really look like any of them, right? We had to sort of make these simplified beds to make the complicated math work. And we tested the physics behind the math, and now we have a really good understanding of the physics. But how do we apply it to a bed that looks like this? It's not sort of typical. You know, it's a combination of all these things and then a bunch of other things. So if we want to actually figure out how glaciers really slide over beds like this, what we need to do is be able to simulate sliding over a bed that has a sort of really complicated geometry, like something that the geology would produce, with all these bumps and smoothed areas and stepped areas and things like that. And so what we do is we want to take a piece of that bed and simulate sliding over. But now that we know the physics really well from the first set of experiments, we're actually going to simulate sliding over with a computer model, right, that has all the physics in it that work properly. But we have to put into the model a bed that has all the characteristics of that thing that we saw in the field. And so we use a new technique to try to generate sort of a replica of the beds that we see in the field. Something called structure for motion. And it's based on a pretty simple concept, right? If you if you have two functioning eyes and you look out at something, your eyes are offset so you can get some sort of depth perception, right? My grad student showed me this trick, which was pretty interesting. It was like, if you hold one finger out and you try to bring one finger in and touch it, you can do it. But if you close one of your eyes, you know, it's a lot harder to line it up because you lose the depth perception. It's the ability for both your eyes to be offset to allow you to figure out distances to things. And so we can take, if you take a lot of photos of something, for example, of this room from all different angles, you could reconstruct what the whole room looks like in 3 dimensions just by looking at the different sort of angles to everything in the photos from a lot of different places. And then if you knew like exactly that this chair was at this place in space, then you could put the whole model that you've made of the 3D bed back into space. And so to do this, the best way to do this is to actually take a drone and just fly it over the region and take hundreds of pictures, like a little quadcopter from the air, and then use all those to reconstruct what the area looks like in 3 dimensions. So this is a cartoon of this drone. It's just flying over. In this case, it's a bluff on Lake Michigan, but we can pre-program in a flight. We can say, all right, drone, this is the area we're interested in. You fly over it, and you take a picture every 10 feet. And then when we do that, we can use all those photos. They're looking at different aspects of the forefield or whatever you want from different angles, and we can reconstruct what they look like at 3 dimensions. And so this is a picture of one of my grad students, Jacob Woodard. He's on one of these forefields where we did this project. So we did this. We went to Switzerland and we went to Canada and we picked 9 different fields because they have different geology, and we think that the geology sort of controls what the bumps look like. And we built really high resolution models of how the fields look, right? So here's him standing here. He's got this control thing, and here's the little drone. So the drone takes off and it flies around, and then we scatter these little like targets around. They're basically bases from a kickball game. And while he sits there and flies the drone, I run around like a madman and try to survey them all in with another grad student. So he's got the easier job, but he's sort of got more liability than the rest of us too. So this is a picture of looking down from the drone. So this is the edge of the glacier, and here's sort of part of the field. And we have thousands of these images. We take thousands of these things every day. The drone flies for 5 or 6 hours, and we're able to map an area that's basically a ½ kilometer by ½ kilometer. One of the benefits, though, of not just flying the drone and walking on the ground is you get to see some interesting things. You're in really remote places at really high altitudes. Not a lot of people are up there. So sometimes you'll come across stuff like this. So these are sort of I don't know if you call them a herd of Ibex or a group of them. So you come across the edge and you'll see these types of creatures. They're not always the happiest to see you. You surprise them. I learned this the hard way. They'll start to hiss at you and sort of tell you to get out of their terrain, which you should do because they're much more agile up there than we are. This is actually a real photo. We hiked up this incredibly steep terrain carrying all this gear, and when we got up there, this guy was playing an Alpenhorn at the top. And you think it could go either way. You could be climbing up the hill and you could be like, oh, this is horrible, I'm carrying all this stuff, and this guy's up here playing this horn, I wish he'd be done. But in reality, it's actually pretty delightful. You know, it like really motivates you to get up to the hill when you see him, and then he'll keep playing it. Of course, he's sort of used to this, so he packs up his Alpenhorn and just flies up the hill while you're standing there waiting for him, or standing there watching him. But it's really nice. Actually, sometimes you find something like this. And so this is an unexploded ordnance. So the Swiss government uses a lot of these really remote areas as target practice for their military. And sometimes the bombs they drop don't blow up, and you'll come across them in addition to other missiles and things like that. So there's some benefit to going around and surveying in these pieces in addition to, I guess, the exercise you get from it. You also get to see really interesting landforms that the glacier has made in these areas. So this is a landform called a Whaleback. You can see these glaciers these rocks are incredibly smooth. Like glacial geologists, will love to see things like this because they're so sort of beautiful in a lot of ways. And these Whaleback features are dominated by abrasion in multiple places. So in this photo, ice is flowing from the left to the right, and you're getting abrasion on the upstream side of the bump as well as on the downstream side of the bump. And it's sort of polishing the glacier up, polishing the rocks up. You can see right here this sort of really shiny area. That's a thing called Glacial College. Another landform that you see a lot is called a Monet. This is a landform where the ice is again flowing from left to right, and you get a lot of abrasion on the upstream side, whereas you get a lot of quarrying on the downstream side. So this tells you that there was cavities here. They were sort of quarrying away the rocks on the backstream side of this over time. So we can use these structure for motion to build these maps that look something like this. So the scale up there is 160 meters. And if you walk through here, every 10 centimeters, so every sort of 3 or 4 inches, we have a data point. Right? So every 3 or 4 inches, we know how high the ground is. We're able to reconstruct this from all these different photos we've taken. And we can look through this to find an area that's really representative of the whole region, maybe something like this, and pull it out. And you can see sort of these are individual sort of rocks on the ground that might be a few centimeters across. So it's incredibly high resolution imagery. And remember, the whole point of this is to take these types of maps and put them into these numeric models so we can simulate the glacier sliding over them to see, do we still get this rate weakening effect even if we have a 3-dimensional bed where there's bumps sort of interacting with each other in more natural ways. And so we've done that. We've taken these models, and a postdoc at Iowa State has simulated sliding over them with a really sort of complicated numeric model. But I'll try to explain just this figure. Basically, this lower region right here, that's this sort of brown color, is the bed of the glacier. This light blue is the bedrock, where this light blue is the bottom of the glacier. So in some areas, the bottom of the glacier isn't touching the bedrock, and that's where one of these cavities is present. But in other areas, the bottom of the glacier is in direct contact with the bedrock, and there's no cavity present. And so this second sort of layer here details where cavities are present and where cavities are not present and how big they are. So this area, that's sort of this brown color, means 0, means the ice is in direct contact, whereas these other areas here have big cavities. So we begin to be able to simulate sliding over 3-dimensional models of a bed that actually has shape to see what this effect is. Is the glacier sort of still producing this rate weakening effect? And somewhat to our surprise, it still is. We still have this process of rate weakening occurring. So initially the sliding resistance goes up, but then as the cavities start to develop, you get, again, this severe rate weakening. Now, we still have to put the really sort of complicated models of what the bedrock looks like in these things, but at least for simpler models, even in 3 dimensions, it still seems to be a prevalent finding, or something we find. So our new finding is that rate weakening slip still occurs over 3-dimensional beds. All right, so if we go back to this original idea that Nye had, Nye and a lot of the original glaciologists were climbing glaciers in the Alps, where we were in Switzerland. And glaciers in the Alps, they slide over a bedrock bed, so the rock is really rigid. But we live in Wisconsin, and Wisconsin was covered with big glaciers. And we know that if we walk around out here and you dig a hole, you're not going to really find bedrock until you go down a ways. There's something else on top of it, right? There's this sort of loose dirt. And this was this big conundrum because people had formulated all these ideas for sliding in terms of hard beds, but in reality, there's another piece. There's oftentimes a glacier will sit on a layer of sediment that can be deformed, and then the bedrock is way deeper than that. And so there's something else we have to take into consideration, is like the glaciers that look like in Wisconsin, where they're sliding over what we call till, the sort of deformed material that's at the bottom of them. In fact, initially this was sort of, people were sort of confused by this, because we knew that places like Wisconsin, which basically looked like the bottom of Antarctica, have till everywhere, but they were like, why is there no till at the bottom of Antarctica? And so then in the mid-'80s, early 80s, a group of geophysicists from the University of Wisconsin started to use different techniques where they'd light off explosives on the ice sheets. The explosives would go down, bounce off the bed, and come back up. And they were like, no, this technique is telling us that the bed of Antarctica is actually made up of this deformable material. It's made up of till. And so then in the 90s, they actually drilled holes through the whole ice sheet of Antarctica all the way to the bed, and it was made of till. So Antarctica, in reality, looks more like Wisconsin than it does like the Swiss Alps, right? So we have to figure out something to explain how ice slips over a deformable bed in addition to the hard bed. And so a deformable bed might look something like this. This is a glacier in Iceland called Mulljökull. These sort of ridges between these dark green things are lakes, right here. And these ridges between them are actually Drumlins. There's features called Drumlins that we'll talk a little more about. And they've been shaped by the bottom of the glacier. The glacier has sort of built these mounds up, and it's dug out other areas. But if you were to look at this material, it's not rock, it's sort of unconsolidated material. And this is probably what Wisconsin looked like 15,000 years ago. There was no plants or anything. It was just sort of a bunch of lakes with debris and stuff like that right after the glaciers retreated out of the area. In fact, Antarctica, when you look at the surface of it, you'd have no idea, but when they drill through, they do see the bed is made up of it. This is just a reconstruction by Dave Michelson and some people from the Wisconsin Geologic and Natural History Survey of how the ice advanced throughout Wisconsin through time. So you can see that this is the driftless area down here. This is the Green Bay lobe. Madison is basically right around here. We built this big glacial lake, Wisconsin. It's going to drain. But the point of this is that as the ice advanced and retreated over Wisconsin, it wasn't sliding over a hard bed. It was sliding over this loose sort of debris at the base of the glacier. And so we need to think about this problem not only in terms of hard-bedded glaciers, like we've done all this work and that a lot of theoreticians work on, but deformable bedded glaciers that have sort of sediment at the bottom of them that can be deformed in addition to the glacier sliding. So we have sort of multiple possibilities for how a glacier might slide over a bed made up of deformable till. The first one here on the left is that the till is deforming as the ice moves over the top of it, and the ice just kind of rides atop the deforming layer. A second possibility, like the one in the middle, is that the till is deforming, but the ice is also sliding at the interface. So both of the things we talked about are till deformation, but all of the things we talked about with respect to sliding before are still relevant. And the third possibility is that the till is actually rigid. It's not moving at all, and that the ice is just sliding atop it. All right, so this would be very similar to the hard-bedded glacier that we talked about before. Now, we know from laboratory experiments that if it's a till-dominated system, if the glacier is riding atop till, the material behaves as something called a Coulomb. It has a Coulomb rheology. Whereas the ice just sliding over the till, like in the third example there, would obey essentially like a Weirtman-type sliding law. And so we have these two possibilities of a Weirtman-type sliding law as the ice slides around little bumps at the ice-till interface, or something that's a Coulomb rheology, which is a little more sort of complicated to think about. Basically, a Coulomb material, you push on it, nothing happens. You push on it a little harder, nothing happens. You push on it a little harder, nothing happens. You push on it a little bit harder, and it breaks. And then once it breaks, you can no longer predict how fast it'll slide based on how hard you're pushing on it, because you can't exceed its strength anymore. It's like a plastic material. So as soon as you break the plastic, it no longer has any strength behind it. So the objective also is to try to determine a sliding rule for these deforming bed glaciers, things like we know they're in Antarctica and like what happened in Wisconsin during the last glaciation. So we can use the same general type of deformational rig. Instead of putting a hard bed at the bottom that has a sinusoidal shape or a step bed, we can put till in the bottom. This is a Horicon till. This is actually the till that we're standing on right now. We run these experiments all over the world. I used to drive to Madison before I worked here to dig 5-gallon pails full of dirt and put them in my car and then drive 10 hours back to sort of run the experiments, because this till that we're sitting on here is so unique that it's perfect for these types of experiments, and it's sort of ideal. So I've been coming to Madison for years, even before I worked here, just to dig things from roadside ditches and whatnot. So this is the apparatus, and that's this Wisconsin till put in the bottom of it. And in addition to putting the till in there, we put vertical strings of plastic beads. And the reason we do that is because after we put the till in, we fill it up with ice like last time, and we twist the ice over the till. We want to see, is the till actually deforming, or is all of this slip occurring right at the ice till interface, or is it something else that we can't imagine? So after they're done, we can pull it out. And this is a chunk of the till that had a string of beads that were originally vertical in them. You can see something interesting here. First, the beads at the bottom have a little bit of a tilt to them, but then there's some gap. There's some missing between the bottom of the ice at the ice till interface and the top of the bead string. And that's because there was beads there, but that till has been deformed so much that those beads have been swept completely out of the picture. And so if I had to sort of draw a cartoon of what the deformation in the till looked like as the ice was slid atop this thing in our experiments, it looks something like this. So the beads are still in the till, they're just a long ways away. And so in addition, you can flip this thing over, you can pull it out and flip it over, so now we're looking at the bottom of it, and you could spend days and days in this freezer that's -10, chiseling it out, trying to find these little plastic beads, and then measuring where they are really accurately to get the full deformation profile, to actually figure out how much deformation is occurring in the till. So I did that a couple of times. And you come up with this pretty simple graph which represents a lot of sort of pain on my behalf, which is this beads you see right here are the things that were at the bottom of the ice. Those are the things that were in that picture. These beads were ones that couldn't be in the picture because they had slid too far away. This red dot represents how far the ice moved totally. And so what you're seeing is that this amount of deformation right here, up until this point, occurred from the till actually deforming, and the rest of this gap between this point and this point is from the ice actually sliding over the till. We can look at the till, and we see some interesting things. So you can probably see a break right here between the till above it sort of has these linear fissile cracks in it, and the till below looks normal. And this is something glacial geologists have used for hundreds of years to try to denote till that's been highly deformed from till that just wasn't deformed. And they were just more or less sort of using intuition or guessing about it. But these laboratory experiments confirmed that that was a good assumption. They were making a good assumption, and their observation in the field are probably accurate for time, the time they were doing it. But if we step back to the sort of $1,000 question here, is how does the ice slide over a till bed? Because this is really the thing that needs to go in ice sheet models. This is the sliding law that those models need to start to incorporate if they want to be able to do a good job to predict it, because we know Antarctica is sitting on a till bed. We had these two possibilities of a Coulomb sliding bed and a sort of a rate strengthening Weirtman type sliding bed. What our experiments show is that it's actually sort of a combination of both, right? That there's some amount of rate strengthening that occurs up into a point where it reaches the actual strength of that till and the till can't withstand it anymore, and then the till breaks, and then the till governs everything else. So just to sort of put this in a more of a schematic type version, we start with these two. It's actually something like that, right? It's a combination of both of them. And at these slower sliding speeds, before we exert enough stress on the till to break it, we're occurring by just slip right over the top of the till, right? There's nothing going on inside the till. But once we reach this sort of threshold sliding speed, then the till breaks, and the deformation is a response of things occurring in the till and things occurring as they slide along the till. But this, not only does this have repercussions for ice sheet models, but it also describes how a lot of landforms that we see that glaciers build underneath the bottom of them from the dirt that's sort of laying around are built. So if we go back to this photo, if you think of this upper layer right here, right above these beads, this till is being deformed, right? It's being advected out of the screen. But in the experimental setup, just as much till is coming in from the back. So it's staying just fine. But say that we weren't advecting till into this situation. The till was just going out. Well, this chunk of till would go out, and then the whole surface would lower down. And this would be the new ice bed surface. And then this would advect out, and it would go down. And so through that process, you can actually erode the till. You can lower the surface of the till over time. And the other side of the coin is there might be areas where the till's coming in, but it's not going out. So you put till in, it stays there. Then you put more till in, it piles on top, piles on top, piles on top. So there's going to be some areas where you're piling up till, and other areas where you're eroding till. So you can imagine some areas are building up and other areas are lowering down. And this is a good explanation for how we form sort of Wisconsin's most famous landform, the Drumlin, right? Wisconsin has these features all over the landscape. They're called the Drumlin field. And these features form at the bottom of a glacier. So in this picture, ice is flowing from left to right. The ice is building up this mound, and then it flows around it, and it shapes it into this sort of cigar shape. So this is what the Capitol sits on. The Bascom Hill is one of these things. And as the ice flows around it, it's sort of depositing material near the drumlin, and it's eroding material in between the drumlin. They come in various forms. This is another one. The ice is flowing from the upper right to the lower left. This farmer was nice enough to plow it in a way that made it look picturesque, or mow it in a way that made it picturesque for us, but it sort of is building up over time. And if you zoom out and you look at a map of this entire region, you can see that there's literally almost 15,000 of these things we've mapped in this sort of area. It's called the Madison Drumlin Field. There's only one other Drumlin field in the U.S. that's even close to this scale, and I'm told in places like Russia they actually call drumlins Madison Drumlin type, because like this is like the most famous site for them in the world is the one we have around here. And so they formed this whole plain. And so likely what happened is the ground surface was quite a bit higher originally, and through this deformation process we're talking about, ice was advected out of the areas in between the drumlins, and a little bit was plastered on the drumlins, and it sort of was dug down over time as the glacier eroded and eroded at its bed. This is the area we are now. So, you know, we have the big drumlin here the Capitol sits on. We have Bascom Hill. This is the drumlin I used to live on. There was a great claim to fame in my field if you could say you lived on a drumlin. I moved down here now, so I'm no longer on the drumlin, but it was a big disappointment to my drumlin friends. But Madison has a bunch of, Monona has a lot. You know, if you go to Google Maps, you can switch to the terrain view. There's a button on there and you can see it, this type of feature. And so you might imagine an evolution of a drumlin field sort of like this. So we're looking at it from the side and the ice is flowing out of the screen at us. We start with something originally that's pretty flat. And then at a later time, there's been a lot of sort of till deformation here, and the material's been advected out and the land surface has lowered. This dotted line represents the original land surface. More and more time passes and you get deeper and deeper pockets in between drumlins, and the drumlins look taller and taller. They may not actually be going up in elevation from where they originally started. It may just be that the area in between is getting lower and lower over time. And that's probably the most likely explanation for the drumlins that we have in Wisconsin. So you get something like this. Is if you were to draw a line across here and you measured the elevation, it would sort of look like that wavy pattern I drew. So some of the overall conclusions I have about glacier sliding is that drag does not respond like the Weirtman-style sliding law predicts for a hard bed. That this rate weakening response, it's been verified for hard beds in the lab and for three-dimensional, more complicated beds in the field. Deformable beds like we have in Wisconsin behave like a cooling material after you get to the point where that deformation occurs. And that these glacial slip processes are responsible for a broad range of landforms that we see. They shape most of the sort of landscape we see in Wisconsin, and things like the Alps and whatnot are a response to this. So I just want to say Neil Iverson has been my primary collaborator on all these projects. Jacob Woodard's a grad student of mine, and Christian Helenau is a postdoc who does all the math for us. The funding for all this was provided by NSF Geomorphology and Land Use Dynamics program. So I'm happy to take any questions if we have any. And that's it. Yep.
So here in Wisconsin, where does the till come from that this is happening? Is that an earlier glacier?
Yes. And a lot of the till, like the Horicon Till that I talked about, and the Holy Hill Formation Till, they're probably sourced from things like the St. Peter sandstone, which is this big sandstone layer we have. It's the bedrock that is here, and it was eroded by the glaciers, by these processes I talked about, and then pulverized basically until it formed sort of this granular till. So some of it was carried in from, I should have repeated the question. The question was, is the till that we have in Wisconsin from here, or was it carried in from previous glaciers from somewhere else? And the answer is both. So some of it, especially the bigger pieces, were carried in from farther reaches away. A lot of the smaller till was sort of derived from the bedrock that was here, that then was ground up and sort of put into place. And probably before the glaciers ever advanced in this region, 2 million years ago, something like that, the region might have looked like the whole thing might have looked like the driftless area, and there already was sediment on there, and it was sort of remobilized and things like that. So, in fact, the Yahara Lakes, the chain of lakes, they're actually a very old river valley that was something like 400 feet deep. So if you stood on Picnic Point, you could look down 400 feet into a river channel. And what we see is the lakes now is just the channel was filled in by all of this deformation of sediment. And the lakes are just a couple of places where it didn't get filled in. And so we know that a lot of material was here probably before the glaciers got here. And it probably reused that, moved it around, it ground up whatever bedrock it could find, all of those things to make the till that we see. Yep.
So when I watch custard coming down out of the Culver's machine, sometimes you can get a galloping custard, and I wondered, is there such a thing as a galloping glacier that either because it's coming down and then it gets a steeper part at the front end actually breaks away from that, or that you get a really, I don't know if you can have a slow-moving avalanche or not, but is there anything like that that people know of, that the leading edge of the glacier actually speeds up compared to the tail end, and you get a separation?
So the question was about Culver's custard, and if we can see similar sort of basically breakups in the ice, and the answer is yeah. What happens a lot is that all these diagrams I showed was that the ice was moving over a bed that was completely flat. But in some areas, the bed will go up on a really big scale. And the ice will have to basically speed up to get by those bumps. And so as it speeds up, it stretches out. And we'll get big cracks on top of these areas where it stretches out. And you'll see crevasses on the surface of glaciers. And a lot of the times when you see those crevasses, they're the result of something like this, of the glacier basically stretching itself apart faster than the ice can accommodate, and then it starts fracturing the custard or the ice apart, and then it becomes like unsafe to walk on the glacier and things like that. But it's essentially a similar type of process of the ice stretching too fast for its own good.
Are there any videos of stuff like that? I mean, I know you see icebergs calving when a glacier comes into a body of water, but is there anything like that?
Yeah, so there's one very extreme example of when this happens, and there's some types of glaciers that are called surge glaciers, and the surge glacier will basically go very slow for like 20 years, and because of some of these dynamics I'm talking about, like at the bottom, it'll switch, and then for 1 year or a year and a half or something, it'll go 10 times or 20 times or 100 times faster than it normally does, and because it's moving so fast, the glacier stretching all over the place and compacting all over the place, you can see sort of crevasses opening up on like a daily time scale. So it wouldn't necessarily be that you would sit there and watch the whole thing disintegrate, because it's never moving that fast, but it's moving many meters a day. And so if you sat there for a day, you would see things open up and close and crevasse in these surging glaciers. That being said, this process of surging glaciers depends on sort of an overabundance of snowfall to occur high in the glacier. And as the climate's warming, that's becoming less and less common. So a lot of glaciers that are sort of classically surging glaciers and probably have surged for like, millennia are starting to stop and surge now. So the one glacier, actually this glacier right here, this is a surging glacier. And last time it surged was a mini surge in 1996. And now we don't think it's going to happen again, just because it's sort of deflated so much that this mechanism's essentially turned off. Yep.
I read somewhere that the glaciers were as thick as like a mile or 2 miles thick, and it would seem like that would cause tremendous pressure on the bedrock or the till. And I'm wondering if that would cause heat with the friction and the pressure, and if that would have an effect on the rate.
So the question is, the extreme thickness of glaciers, does that cause a lot of pressure and increase the sort of frictional heat that's generated as the ice is sliding over? And the answer is everything you said is right. So the ice was that thick. It severely depressed the crust. The heat that's generated by the ice sliding over the bed is a function of two things. If you put your hands together and you rub them together, but you don't press them very hard and you rub them slow, you're not going to heat it up. If you press your hands together really hard and you rub them really fast, your hands start to heat up really quickly, right? And a glacier does the same thing, especially if there's a lot of debris at the base. So if there's a lot of sort of friction or contact between the debris and the bed, and the glacier's moving very fast, it can generate so much heat that it actually starts to melt the ice at the bottom of the glacier. And so a lot of these regions that move quickly in Antarctica are because that process is happening, and it's generating enough melt to essentially keep the base lubricated. And if they ever shut down for long enough for the melt to freeze up, it's very difficult for them to get started to move again, because they sort of lose that frictional heat that they're generating from the ice sliding over the bed.
Can you give us a prediction of how your models will predict climate change in the future?
So the question is, how will my models predict climate change in the future? The answer is my models won't predict climate change in the future. What my models are good for is if somebody tells us what like temperature should occur or what types of climate you might be able to expect, I can tell you how much faster, or not right now, but once we fully develop these models in the future, we'll have a better ability to tell you how fast or slow the glaciers go. So, and why that's important is it will tell you what the sea level rise is. So these models don't really predict climate change. They're just the link to get from climate change to sea level rise, essentially.
And isn't the implication of your work that the climate models have underestimated
Could you say it a little louder?
Isn't the implication of your work that the climate models, like the IPCC uses, have underestimated or been very conservative about sea level rise?
Okay, so the question is, aren't our findings indicating that the IPCC's estimates may be underestimating their projections? The IPCC models do have built into them pretty big uncertainties because they, like that statement they made, they realize that this is a big shortcoming in their ability to predict. The problem is we don't really know how big of an uncertainty it is. If you look at the IPCC, they'll say if we produce this much greenhouse gas, we should expect this much increase in sea level rise, but there's these huge error bars on them. The reason that those huge error bars are on there is part of the reason is because we don't know this that well. What this would allow us to do is not maybe change the is to reduce those error bars and be more certain that if we traveled along this trajectory of emitting this much greenhouse gas, this is how much sea level rise we'd be able to expect. And instead of saying, you know, it will go up 1 meter plus or minus a meter, you could say it'll go up 1 meter plus or minus 3 centimeters or something. It'll sort of shrink the error on
it. But isn't the implication of your work that it's not non-linear, and at some point you might just suddenly lose an ice?
Right. So I will say this: the implications from this work, it says that if the bed is the only thing holding the glacier back, it's nonlinear. But I suspect, and in reality, there's other things that aren't incorporated into these models that are holding the glacier back. For instance, the glacier dragging on the sides, or in Antarctica, there's not really sides like we think of like rocks. The glaciers are actually connected to other ice. So we have another project that is looking at how much the ice can hold back the glaciers. And so there's other components to this system that we still need to develop the physics for. And traditionally, a lot of it's been, or almost all of the ability for the glacier to hold back, be held back, has been attributed to the bed. But I think there's other things that we haven't taken into account that are important, that'll sort of feed back into the system and provide stabilizing. And the reason that intuitively that has to kind of happen is because we don't see glaciers shooting off the mountain. Occasionally, it does happen, like in the Swiss Alps and things like that. A whole glacier will slide off a mountain, and there's been instances where it's basically killed everyone in towns. But that's a very rare exception. And because of that, there has to be some feedback mechanism that we don't currently incorporate into our models that sort of balances the system out.
Can you tell me what's the range of strength and tensile then of ice? I've never thought about that much, that ice has got to be strong in tension, not just in compression.
So in compression is the way we normally think about it. The compression strength is about 1 to 10 megapascals, and in tensile it's actually less than that.
How much does it range depending on the composition of the ice?
A lot. In particular, it's really important if the ice already has cracks in it. If there are already little cracks in it, which there almost always are, because the things that we were talking about, like the ice stretching out and squeezing, like the Culver's analogy, those really reduce the strength and tension in particular. So it gives sort of seats for the ice to sort of break as you're pulling it apart. Yep.
There are some physicists who've been talking about various ways of increasing the reflectivity of the sun in order to decelerate climate change. What are the analogies coming from your research about ways to decelerate the melting of the ice?
So none of this is my work, but there are people at our meetings that sometimes present ideas. And the one idea that's been presented most recently, and it was covered in CNN a couple of weeks ago, is these are all sort of pie in the sky types of ideas. But the one idea is that in a lot of areas that are destabilizing, it's because the ocean is warming, and the ocean is melting away the fronts of the glaciers. And it's kind of counterintuitive, but in Antarctica, the warm ocean water is deep. It makes sense because the climate's so cold there, the surface water would be really cold. So this warm ocean water comes up from a greater depth, and it starts to sort of melt away the fronts of the glacier. And if you melt away the front of the glacier, it can be very problematic and lead to a very rapid retreat. And so one idea has been to essentially build a giant seawall in Antarctica that can protect this one sector that we know is it's been termed the weak underbelly of Antarctica. I'll try to go back to this map if I can find it. But there's one glacier in particular in Antarctica that's extremely important. It's probably the most important glacier in the world because it can lead to the destabilization of West Antarctica. It's this glacier right here. It's called Thwaites Glacier. It's named after Freddie Thwaites, who was a glacial geologist at Wisconsin, and it's a big deal. This glacier is a big deal because the ground slopes backwards towards the center of the continent. And if it gets over this hump, or it starts to slope backwards, because of these runaway processes that we've been talking about with sliding and things like that, and also ocean melting and calving, it can lead to a runaway collapse of Antarctica. At least that's a potential. That's something that's been modeled. But the whole thing gets triggered because the ocean melts the front of it. And so one idea has been to build a giant seawall in front of this glacier to stop the warm, deep waters from getting to the base of the glacier and melting it back and destabilizing it. It would cost, I think the estimate is conservative, trillions of dollars. It's highly skeptical. Who knows if it would work? But I think we need to have ideas like this. Like, it doesn't hurt to think outside of the box and try to investigate these types of problems. The other one is, so one of these glaciers I talked about, this isn't functional on a long-term timescale, but one of these glaciers, what we worked in the Alps, they're buying these giant white canvas tarps, and they're laying them on top of the glacier. And that's to sort of reflect more of the sunlight so that the glacier doesn't melt. And I didn't believe it until we went there and saw it. It looks totally bizarre. I mean, it's literally covered with a giant tarp. But it has worked. That part of the glacier is stabilized. And they did it there for a specific reason, which is they've drilled all these holes through the glaciers that you can walk through, and it's a tourist attraction, and they didn't want it to melt because it cost them a lot of money to do it, so they put these tarps over to preserve it. Is that functional on a much larger scale? Probably not. You know, you probably need to think something glacier. And it would need to be strategic. You know, you would need to think about something about Thwaites Glacier since it's such an important site. And there's been a giant project funded between NSF and the British funding agency to go out and really try to study Thwaites Glacier. It's probably the biggest Antarctic group project ever proposed. So University of Wisconsin, I'm in it, we're one of the universities that worked on it, to go to this site. So we're going to go out here for the next 2 years and live on that glacier and deploy hundreds of instruments and try to study it as deeply as we can. And our role is to try to figure out what's going on at the ice-bed interface of the glacier. So the project started this year. People are out there right now. Yep?
The glacier formation and receding of the glacier in Wisconsin and bringing the till, depositing probably downwards, does it have any bearing on the agricultural phenomena in Wisconsin? I saw a TV report about 3 days ago, a ginseng producer in Wausau.
Yeah?
He attributes the soil in Wisconsin to the ice age. And then he says that is why Wisconsin ginseng is the best in the world. And he was talking about it, and he attributed to the glacier period. And is there any truth to it, and what is it?
So the question is, how much is the soil in Wisconsin related to the fact that the glaciers were here, and specifically, does it help the growth of ginseng? I don't know if it helps ginseng, but it definitely does. The glaciers definitely influence the soil here. And actually, a lot of the times when glacial geologists in the state of Wisconsin go and map areas, the first thing they go pull is the soil maps, because the different descriptions that the soil scientists have done to describe the soils get us a long way to try to figure out what type of deposits we're looking at from a glacier sense. So that's definitely correct. So if you think of the northern part of Wisconsin, you have all those pine trees and the lakes and the really sandy soils. That's because the glaciers deposited a different type of material there, this really sandy outwash material that was deposited by streams, than when you compare it to the deposits that might be found over by Milwaukee or something, where the till is very, very clay rich and very sort of, it looks almost like lake sediment, but it was stuff that the glaciers dug up out of Lake Michigan, remixed, and then laid down in these thick till units. So the glacier action of digging things up, eroding them, and redepositing them sort of a lot of times directly leads into what types of soil you have. So like in Iowa, the reason that Iowa has such good soils is because, in part because of the glacial tills that were deposited in the footprint of the Des Moines lobe are the sort of right combination of loam, sand, and clay that they need to sort of support plant roots. So yes, yeah. Yep.
I understood that the drumlin beds are towards the terminal moraines of the glaciers.
Mm-hmm.
Is that a result of the speed of it slowing down, or is it something else, or a combination of things? And also that in relation to that pure drop shape is what's the mechanism there?
Yeah. So the question is, if you look at the distribution of the drumlins in Wisconsin, they're primarily located near the terminal, the end of the glacier margin. You don't find them way far north as abundantly, or there's actually a zone right by the terminal moraine about the first 15 kilometers in that you also don't find them. And the reason that people have speculated on this, mainly this sort of my predecessor's name's Dave Michelson, has come up with this really sort of elegant idea, and that's that the reason, if you look at the ground in Wisconsin and the landforms we have here, they look significantly different compared to like if you went to Michigan or Illinois or Iowa or things like that. And that's because when the ice advanced into Wisconsin, it advanced over frozen ground. The ground's already frozen in front of the ice, and so the ice went over this stuff called permafrost. And so the ice, you have to imagine you have this frozen terrain, the ice advances over it. Now the ice wants to deform the till. The till is still there, but it's frozen. Some areas start to melt, and other areas stay frozen. And the areas that melt are easily deformed, like I did in the experiment. But the areas that didn't melt, that stayed frozen, they are much harder to deform. And so the areas that were frozen essentially formed the nucleuses of the drumlin field. So everywhere you see a drumlin, the idea is that the core of it was basically frozen and left over, and that made it more resistant to deformation and erosion, whereas everywhere else that was sort of dug down, the ground was thawed out and easily eroded. And is that your whole question? Okay.
And the shape of it?
Oh, the shape. Yep. So the shape is largely comes out of essentially fluid dynamics. If you look at drumlin, the ice moving around it wants to sort of sculpt it into this sort of elongated shape that's the least resistance to flow. It's kind of like you build an airplane wing or a bird's wing a certain way because it's the least resistance to airflow moving around it. Well, the drumlin's kind of like that. It's a little bit different because it's ice which basically behaves like a fluid similar to air moving around a granular material, and also the granular material can be moved, which is they normally probably what happens is they normally start out as these more rounded features, and over time they get skinnier, longer and longer and longer. So that map I showed of part of the drumlin field, if you look, you'll see somewhat systematic variations in their length and width. These drumlins up here are very long and skinny. These drumlins down here are a little shorter and fatter, things like that. So that means that these drumlins probably had more time under the ice and more time to sort of transform to these short, squat ones to these long, skinnier ones. And that makes sense because they're further to the north. And as the ice retreated, you would have expected areas to the further north to be under the ice for longer. And so this sort of stream, this elongated shape is largely a ramification of the ice reshaping them and the amount of time they had under the ice to be reshaped. Yep.
Question about what is the ratio of time with the real slip compared to the simulator slip?
Great question. So the question is, what is the ratio of the time of the real slip to the simulated slip? These glaciers were here for tens of thousands of years, 60,000 years, let's say. The experiments run for 3 months, so there's no similarities between the time scales. But what we're able to do is run the experiments to something we call steady state. And that means that we run it long enough that things aren't changing. And if you had a long enough period of time and you just kept running it the same, if we ran our experiment for 60,000 years, things would basically keep becoming the same. And that's the importance of this experiment, is that we can run it long enough to get to steady state. That takes us weeks, right? So if we couldn't run the experiment for at least weeks, we couldn't be confident that what we were doing in the lab could be applied to a longer time scale. But because we can, and we do get to this steady state where stress isn't changing, we're not sort of shortchanging ourselves. That time where it gets from the original state to the steady state, this what we call it a transient period, is extremely interesting. It's something that's basically not studied at all in glaciology because it's so hard to fathom how to put this thing in there. And before we started doing experiments like this, there is basically no way to even guess what was going on, just because we don't know, the forces don't balance. And a lot of what we do is essentially trying to balance forces and stresses. And in those periods where the forces and stresses aren't balanced, it's a chaotic world, and the math and the physics become a lot more complicated. So the experiments they're fine because they get to steady state, but the next realm, the really complicated stuff, is when they're that sort of couple weeks or couple days or maybe even a couple hours when things are changing before they get there.
And then, if I get one other question, are there any variables that have a more exponential effect on the slip than others, or is it predominantly they're all pretty equal within that aspect when you consider the length of time? So
the big variable, the question is there one variable that's more important than others with respect to the slip and that can change in time? There's one variable that's extremely important, and that's what the water pressure is at the bottom. So there's actually water, liquid water at the bottom of the glacier, and it's under some pressure. And most of the time, the pressure of the water is almost equal to the pressure of the overlying ice. They're almost perfectly in balance. So if you drilled a hole to the bottom of the glacier, the water would come up almost all the way to the surface. It wouldn't quite overflow the surface. Sometimes it does, most of the time it doesn't, but it would almost be there. And that fluctuates around really closely to that overburden pressure, the weight of the ice. If it's a little over or it's a little under, the mechanics become very different one way or the other. And the water pressure can change on a pretty fast time scale. Like if you had one of these crevasses that was a pipe basically from the surface to the bottom, and you got a rain event at the surface, or a melting event, and water started to go through this pipe to the bottom, it could push the water pressure up at the bottom. And you could see very drastic changes in how the glacier slides and how the glacier responds. And so one thing to be concerned about when I talked about how melting isn't the main way a lot of these big glaciers lose mass, is if there is actually melting at the surface and then that water makes it to the bottom through crevasses or moulins or things like that, it can seriously affect the water pressure at the base of the glacier. And that can have really big repercussions on the dynamics of how the glacier flows, of how it moves. And so I've said this before, but my goal by the end of my career is to solve the problem of glacial slip, right? What we talked about here, to figure it all out. But at that point, all I basically have done is said, we figured this out, and I've turned it over to the hydrologist to say, now it's your problem. Yeah.
We talk about glaciers advancing. It's kind of a bulldozer because the leading edge is actually moving. When we talk about retreating, does the leading edge retreat or does it melt in place? In other words, does a rock move backwards, back up towards Canada on a retreating glacier?
Yeah, that's a good question. The question is, when a glacier retreats, does the margin of the ice just move backwards, or does the ice actually move backwards? The answer is the ice never moves backwards. It's always the edge moving. The ice only flows downhill. It only flows towards the front of the glacier. And the margin retreating is just because the ice that's feeding the glacier can't keep up with the melting that's occurring at the front. And so ice will never flow back up a hill, just like a river would never flow back upstream.
So are your models just in a static condition, and if there's a dynamic condition, it's another ballgame?
Exactly. So the question is, are the models just a static condition, and if it's dynamic, is there other properties that we haven't accounted for? all ice sheet models are effectively solved with this idea of these physics being in a static sense. And all the results I've shown here are jumping from one static position or one steady state position to another steady state position. But if there's dynamic effects or transient effects that occur during these weeks where we transfer between one state to the next, those problems are very hard to solve. The next project, the project I'm working on right now, so this summer I'm hosting a meeting in Madison for the International Glaciological Society. We're getting all the glaciologists in the world who care about this to come to Madison. And the point of my talk at this meeting is to try to address those types of concerns, these dynamic concerns for the first time, to try to test how relevant they are. And frankly, the only reason we can do that is because of these advancements we've made with our experimental techniques. In the natural setting, it's very hard to tease out or separate the variables to figure out what's important and what's not important and how things are changing. One thing changes relative to another. So it's really hard to get at what the fundamental properties are. And it's with these experiments that we can begin to sort of dig into the dynamic properties and try to investigate them. But that aspect of glaciology is in its very infancy.
Any other questions? If not, thank you very much.